get started. Yeah, I don't think it's technically morning anymore. It's more like the afternoon. Well, depends on when you woke up today. How you folks are doing? I was test on Wednesday. Decent, very fair. Okay, yeah, and break is just around the corner. I can't wait for the break too. This test was most fair test so far. Questionable. So not everyone liked it. Um, this test on Wednesday. All right. So yeah, and it's Friday, so lecture 23. Welcome. Let's organize some computers. And someone is asking about their textbook problem. So I caught up on pretty much everything. I thought, and so all rainbow grades are updated, and everything that has been submitted is graded except for, of course, test 6, the most recent test. But our TAs are fantastic. They actually did. They put in a lot of effort and they graded everything. So we do not have any backlog of ungraded stuff, which is, I have to tell you, is kind of rare in this class. So this class is harsh not only on students but on teaching staff as well. But our team is great, so they caught up on everything, and they are working on test 6. So we'll be working on test 6 over the weekend. We haven't really started, but we will make some progress over the weekend. And so I caught up on all their rainbow grades stuff, and all their all the panelists should have all their points updated as well. And someone is asking me about their first textbook problem. This is 4.5. I was going to look into that, but I didn't have a chance to. So I was investigating that what's wrong with it. Problem clearly, it looks like something is wrong, and it was brought to my attention by a student back on Monday or Tuesday this week. So I will look into that. I think I have a pretty good idea of what happened. I think it's a copy paste thing. It's a copy paste error, believe it or not. But I need to verify it. So I have a suspicion, but and I think, as you know, our textbook has different versions for different architectures, MIPS, ARM, at least 2 versions. So what I think happened with 4.5 is our professors Patterson and Hennessy, the authors of the textbook, I think they just grabbed their problem from their ARM edition of their textbook and put it in this MIPS edition. And it is only the problem with this sixth edition. So I checked back fifth edition, and the problem was slightly different, but it was correct. It was from the MIPS edition. So this one, 4.5, definitely doesn't look right to me. But like I said, I need to look into that further. I will do this hopefully over the weekend. Of course, I will let you know. And we either post a correction to this problem, or we just say let's scrape this 4.5 and just remove it from the homework. So just stay tuned for announcements, and we will let you know what the status of this 4.5 is. Someone says they have open grade inquiries. Yes, please email our head TA Niha with any stale grade inquiries, and she will either take care of them herself or she will get one of the other TAs lined up to close those grade inquiries. We are trying to stay current, but sometimes things fall through the cracks, and we are less than 4 weeks from the end of the semester. So clearly, please check all your older grade inquiries, and if anything has not been resolved, then please certainly let us know. Do you think we will have test 6 before the break? I seriously doubt it, because that would be that's I don't think it's going to happen. So we will definitely have test 6 before test 7. Okay, so that I think is definitely likely. Yes, the biweekly exams are rough for TAs, and for the instructor, for your instructor as well, because that person needs to write those exams, and then on all exams we have people who are sick or have other excused absences. So I have to write a makeup exam in addition to that, and of course it has to be different from the regular exam. So and then I have to write all the solutions. So it's very taxing. So I regret that we have 7 exams, but it's too late to change anything now. But something for me to uh, you know uh, to keep in mind next time next time around I teach this class. On the test, yes, there were 25 points per problem, and yeah, someone's saying it's 4.5 from the text from their homework as extra credit. No, that's not going to happen because if it's a broken problem, then it just needs to be either fixed or removed. There's no point of of expecting people to know if it is indeed what I suspect it is, and it's just from the ARM edition, then it would be completely unreasonable for anyone to solve this problem having ARM ISA in mind instead of MIPS. So, but like I said, it hasn't been decided yet. So let me look and verify. Yeah, only one exam left, and yep. So we are almost done, and you can always skip an exam or two. I don't know. It's kind of getting close to the line that I don't think we are allowed to cross. Right? If the decision was made in the beginning, then it would be another story. But since we advertise 7 exams, some people might say that, oh, I don't want fewer exams because then each exam would be worth more. And maybe they're hoping to get more credit on exam 7, and if we just cancel it, those people are not going to be happy. And I can understand why. So for exam 7, take it easy and give us a bunch of simple word problems. Well, I'm thinking about making exam 7 easy. Okay, so I don't know, as easy as exam 6, but something, I don't know, hopefully something manageable. All right. And several people asked me already about any incentives for dropping something, lowest homework, lowest lab, lowest exam. So and yeah, so as I mentioned before, let's discuss this when we are back from the Thanksgiving break. Okay, and one reason I don't want to discuss it now is because I actually want people to do all the work and then have this drop something as an extra treat. Because if you announce it too early, then people would be like, oh, since this is going to be dropped, I just not gonna you know attend the last exam or do the last homework, something like that. So I don't want this to happen. So I view this, drop something thing as an extra treat, as a way for people to, have their occasional hiccup with one of their gradables fixed, and not as a means of, skipping something at the very end of the semester, because all topics are still important, all topics that we are going to cover. Well, not drop an exam, but we are thinking about dropping, some lowest grade. So no, so we're not canceling their, anything as of right now, at least. Okay, and I'm just trying to catch up with. All right, yeah, and as usual, as you have seen in this class throughout the semester, if there's a choice of what we want to do, then of course I will run a poll. All right, so I think that's it, and today we are in week 13, 15. So uh, yeah, we are a little behind again. As compared to our original plan. But again, I checked the schedule from last semester, and we are just one lecture behind from where they were in the last semester. So I think it's kind of normal. So I'm not particularly concerned. Right, the last topic that we have, like the parallel programming is really a high-level introduction, so I don't think we would need to spend as much time on it as we initially were planning. So if you look at our initial course plan, then there's like 3 or 4 lectures on parallel programming. So I don't think we need to do that. So I think we are more or less okay, and I think given the choice, I would rather skip parallel programming part, because if anyone is interested, they would be able to take parallel programming in a dedicated class, which is, by the way, great. But the stuff that we are going through right now, the pipelining, and then our next topic, memory, this stuff is really important. So I would rather spend more time and make sure everybody, or at least the majority of students, are comfortable with the pace, and I'm not like trying to rush 200 slides lecture. Okay, and I was going to share something. So let me see what I have as my plan for today. So yeah, lecture 23, TGIF. Hopefully everyone is enjoying their Friday, and we have panelists. Let me check our Q&A to make sure that our panelists are there. All right, I only see one panelist though who responded to their test question. So if other panelists are here, please respond, answer something to this test question, and then just answer other real questions that hopefully will be popping up. All right, and so test 6 being graded, homework, we moved their deadline, so I think everyone should know that by this time. And projects, remember today is the deadline for forming your teams, and we will run a poll on on the best name for the team. So please come up with a creative or not creative, just with any name, and then we run a poll for the best name of the team. All right, so make sure you declare your team today, tonight, if you haven't already, because there will be no extensions. All right, we don't have much time to. We have to have all the teams formed tonight by by the end of the day today, tonight, and then just people start working. Well, hopefully all the people have already started working. So all the teams that have already been formed, hopefully they at least gathered once, maybe even twice, and started working on the project, because it's even with 5 people on the team, it's still a fair amount of work. Okay, and one other announcement that I wanted to make. It is related to submitty. So submitty had an issue. Well, it was actually not submitty's fault, but their feed that the submitty gets from the registers got broken, and submitty reported that like 80% of the students lost access to their courses on submitty, and it has been restored already, but there still might be some quirks. So if you notice anything, anything weird, or you cannot log in into any of your classes on submitty or something like that, please please let them know. Okay, so they think they fixed everything, so they just reverted to their feed from 2 days ago, which was not broken, but just in case, wanted to mention. Okay. Well, like I said, I don't think it's a submitty fault. So let's be fair to submitty, right? It has its own bugs, but this one I don't think is on them. I think it's on the registers more than on submitty. Okay. And yeah, so let's go then just through our slides. And I don't know, I have an ambitious goal. We have about 100 slides left in this chapter 4. So I will be trying to go through all of them today. I don't know if it's realistic, probably not, but we will try. Okay. So we were, and here I am. And by the way, one other thing that I wanted to mention. So we have, I also caught up on all the late days. So I think I've run Rainbow Grades, and it collected all their polls that we've had so far and computed all the lay days. And so those should be accurate now with the latest update of Rainbow Grades. So please check and see if you notice anything, anything weird, or you think you're missing any points for any of the polls. Please let me know. But I checked, and there are a few people who are currently at 7 late days for the entire semester, which means they earned 4 extra late days in addition to 3 late days that we gave everyone from the start. So, and that kind of sounds about right. So we had like 69 or 68 balls. So some people were able to get 60 points from those 69 balls. So it's a pretty good ratio if you think about it. So 7 late days is kind of nice. And so we're gonna have, I have 4 more balls planned for today. I don't know if we cover enough material to get all 4 of them, but like I said, I'm going to try. And by the way, something that we also discussed, just wanted to remind you that we agree that for this test, one problem will be extra credit. So essentially, their test will be out of 75 points. So there's like a 25% you know uh, up margin if you will, and so of course there will be no further curving, and we did curve test 5 if you noticed. Okay, so with this extra credit that we had on 2 exams earlier and that we are going to have on test 5, so we still have people who are, well, we do have people who are above 100% so far in as far as their standing in this class. So those people earned more points that were officially awarded. So some people are above 100%. So kudos to those people. So good job. It's really impressive, and I expect more people will join that elite group once we grade test 6, because I think it was reasonable, and with 25 points extra credit, I think more people will be able to score over 100%. So we were discussing our pipeline idea, and that sounded like a very cool idea. And hey, we can definitely increase the throughput, which means our instructions will execute faster. So not each individual instruction, but on average, we are going to have more instructions executed per unit of time. And of course, that comes with certain complications. So we have to face a problem, or well, a general problem that we called a hazard, and then we classify them into 3 types of hazards, and then we were trying to decide how we combat those hazards. And so that was the example that we reviewed, the hazard that we called data hazard, associated with the fact that the value that we need to read from a register hasn't been actually written to that register by a previous instruction. And therefore, we had to stall the pipeline, and then we kind of sketched a solution to this problem that we called forwarding. And the idea was, well, yes, the value technically is not yet written to the appropriate register, but we don't even need it to be in that register. As long as we know what that value is, we can, kind of take a shortcut and fast forward this value to the next instruction. Okay, so and that was the idea behind forwarding that we discussed. And IF is instruction fetch. And I recall someone was asking in one of their previous in one of the previous lectures, like, do the compilers need to do anything about forwarding? And my answer was no. Forwarding is purely a hardware feature, and the processor has to. And it was also a question about their stalling the pipeline or all those bubbles, right? Do compilers need to do anything about it? And the answer was still no, because the processor has to ensure that each instruction, if it's a correct instruction, it is correctly executed. So it is the processor's responsibility to add bubbles to stall the pipeline if it needs to ensure the correct execution of any instruction and all instructions that we feed to the processor. That said, with a strategic placement of instruction, which is something that compiler can totally do, we can actually help the processor to avoid the necessity to do stalls. And that is the technique that is called code reordering. So the idea is, in many cases, or at least in some cases, we can reorder our instructions as to avoid stalls, but at the same time without changing the net effect of the code. So the code would run with the same effect. So after executing a piece of code, the state of the processor and all the memory and all the registers is going to be the same as before modification, but the modification allows us to avoid stalls. And here is their example. And so originally we have this piece of code that is just MIPS for the C code given here. So just two assignments, this one and this one, and we load the values from memory into T1, T2. We add them, put the result in T3, and then this is our A, and then we store from T3 into the actual memory. So this is our A, and so this is our B and F, and let me see. T1, I believe, is B. Uh, so T2 is going to be E, while the loaded values. All right, and then this one is going to be F, right? Please check my logic. If you see that I mess it up, please correct me. So, and here it's just straightforward, right? It's something that you would have done in your homework 5 when we asked you to translate those assignments into MIPS code. And we see the problem, like, here we are loading into T2, right, which is our E. So we have to read E from memory, put it in a register. And the immediately next instruction is we have to read this T2 because we are performing our addition. So clearly, this is a load use hazard, and the processor, when executing this piece of code, would have to insert a bubble. And the same thing happens with T4. So here we load F into T4, and then the immediately next instruction is reading T4 because it needs to perform the second addition. All in all, it's going to be 13 cycles, right? If we consider the bubbles, the stalls, and it turns out that we can do better. It turns out it doesn't matter which order we load B and E, and well, not B and E, right? But we can rearrange our instructions so that we load T4 in here, right? So that we load our F in here. So like in here, right? We can do our F, and yes, F is not going to be used for a while, but that's exactly the point why we want it here. So note how this instruction that loads F into T4 is moved to instructions up. Okay, and yes, we don't need F here, but that's exactly the point. All right, we don't need it here, but it allows us to have this strut between the instruction that loads E and that reads E. Right, so this T1 thing, right, is T2 thing. Sorry, T2 thing is now not the immediately two adjacent instructions. They're now, broken. They're now separated by this extra instruction, and previously we would have a stall here, okay, which was just a waste of time. But now we are doing something that we will need, right? Yes, a little bit later, but it's still useful work. It's still an instruction that has to be executed, and we just moved it here so that we have one instruction between load and use, and that allows us to avoid the stall. And that same thing that we did actually allows us to have to eliminate their hazard on T4, because now it's not like we load F into T4 and we are immediately reading T4 to perform our addition, right? We have even two instructions that separate those, and that allowed us to save 2 cycles, and we can, this whole code executes in using 11 cycles, okay, because we were able to eliminate 2 bubbles. So this is just the ordering of instructions. It does not change the semantics. It does not change the result of executing this code. Meaning that when we reached this part, right? When we are here, the state of their processor and memory, so all the registers, all the memory values, is guaranteed to be the same as here, as when we executed all those instructions and reached this point. So that means that these 2 pieces of code are equivalent. They're not the same because the instructions have been reordered, but their net effect is there is no net difference, right? So the state of all memory values and all register values is the same at this point of execution. Okay, which means that we can do it, right? If by reordering instructions we changed the final state of the processor or memory, then it wouldn't be a valid reordering, because it means that 2 pieces of code work slightly different. All right, so that was our first introduction to forwarding, and we will have a lot more of it coming up when we actually talk about how do we implement forwarding, right? It's going to be not exactly trivial, so it's going to be a complication that additional stuff that we will have to add to our data path diagram that we reviewed for our simple example. So now soon you will see why that example, that we had at the end of our lecture last Friday was called simple, right? I say quote unquote simple because it wasn't that simple, but compared to what we are going to see, that one was of course much simpler. All right, so that was first type of hazards, data hazards. So the second type, recall, were structural hazards, and we said we cannot really do much about them, right? We cannot really fix them except for changing the design of our processor, like separating memories or making some other changes to the hardware. So we're not going to be talking too much about structural hazards anymore, because there's not much we can do. And the third type, although control hazards, it turns out that this is something that we can, try to combat. And it's like data hazards. We can come up with some ideas of how to minimize or how to, make control hazards less affecting the performance, right? Because any hazard, it affects the performance by making those bubbles. A bubble is essentially a placeholder for an instruction, and we will call it a NOP, no operation instruction, an instruction that does nothing, that doesn't change the state of the processor or memory, but it takes up time. It takes up the slot for the instruction, and of course, in that sense, it's a waste of time. And of course, we want to have as few hazards as possible, as few bubbles or NOPs as possible. So control hazards, just a reminder of the definition. It is their hazard, it is their condition where we have to insert bubbles due to their branching or jumping, due to the changes in their flow of control. So a typical example would be our BEQ instruction. Imagine you are fetching your instructions, and then an instruction is BEQ, and then you are like, all right, what is the next instruction that I should fetch? Is it the instruction that follows immediately their BEQ instruction, or is that the instruction that BQ label points to. The label in the BQ instruction points to, and hopefully you had some fun with on test 5 with it was exactly a BQ instruction there for a reason, because we want to use your knowledge of how that instruction is executed and how it was executed in a single in a non-pipelined data path. This knowledge would allow you to understand our topic today. Okay, if you don't know how instruction BQ works and how it is processed, how it is executed by the non-pipeline data path, it's going to be very challenging to understand the control hazards topic in a pipelined processor. Okay, so recall BQ has two registers and a label, and if register values are the same, then the flow of control will be passed to the label, to the instruction that is labeled with that label. All right, so we say that this is the case when the branch is taken, and if the values of the registers are not equal, then the branch will not be taken. So their next instruction to be executed would be the next instruction after the BQ, just linearly, literally, PC plus 4 kind of instruction. So that obviously creates a problem when we are fetching our next instructions after BQ. We don't know whether the branch is taken or not. And that explains why the pipeline can't always fetch correct instruction, because it doesn't know in advance whether the branch is going to be taken or not. So the key observation here is we need to know this decision whether the branch is taken or not as early as we can, so that we can, decide, or the pipeline, we can instruct the pipeline which instruction to fetch next. And, if we just think about this in general, like at which stage do we know if the branch is taken or not? Based on what we discussed for a non-pipelined data path, which component is responsible for deciding whether the branch is taken or not? Control. Well, branch 0 or 1, no, because branch is just the control signal that says whether it's a branch instruction or not. So this branch coming out of the control ellipse, it's just one for all branch instruction, BQ, B, BNE, whatever. So it by itself does not tell us whether the branch is taken or not. It's exactly the 0 output of ALU. All right, so ALU subtracts the values read from two registers, and if the subtraction is 0, if the result of the subtraction is 0, meaning that the output, that sum or result output of ALU has all zeros, then the 0 flag, the 0 control signal, is going to be 1, saying yes, it is a 0, and that 0 is indeed routed to the AND gate. So 0 AND branch, if both of them are 1, it means the branch is taken. Exactly. So we and obviously now translating it back to 0 equals 1 only in CS. It's very common. So just get used to it. That means so our ALU now in the pipelined architecture, which stage is it? Anyone? So the ALU, yes, EX, thank you. No, MEM is memory, okay? That's the data memory, right? Not even instruction memory, data memory. So EX, at EX stage, our ALU, well, it works all the time, right? But in our pipelined, slicing of the instruction, we see that, ALU is at the MEM stage, at the EX stage. You got me with the MEM. At the EX stage, of course. And that means that if we have a BQ instruction, we will not know whether the branch is taken or not by the end of the third stage, okay? Because we have IF, ID, and then EX, right? So, and that is pretty late in their instruction execution cycle, okay? So we want ideally to know it sooner. And we can throw in additional hardware to do this at the ID stage, right? But we have to throw in additional hardware. If we don't do that, then we can only determine whether the branch is taken or not by the end of the third phase of the third stage, by the end of the EX stage. So why is it feasible to, why can we hope that we can, throw in additional hardware and do the comparison at the ID stage? Well, because we cannot do it any earlier than the ID stage, because to decide whether the branch is taken or not, we need to know the values of two registers. Okay, so that means that registers have to be read. It happens, as we know, at the ID stage, and so then if we read the registers and have an additional ALU, or it's going to be a specialized ALU called comparator, right? That just compares two values, whether they're the same or not. And if we throw in this additional component into our diagram, then yes, we would be able to tell whether the branch is taken or not by the end of the ID stage. So it doesn't sound like a whole lot, right? It's just one stage earlier, but actually the effect is pretty noticeable, right? Because we only have 5 stages, so even one stage earlier might be a difference between stall or no stall, and that is valuable. Okay, so that's our idea. We need to compare registers and compute target early in the pipeline at the ID stage instead of their EX stage, which would be our simple existing solution. All right, and here is an example of the multi-cycle diagram that shows what happens with our pipeline when we have our branch instructions. So why is it called multi-cycle? Is there a single cycle? Yes, there is a single cycle diagram. This one is called multi-cycle because it shows multiple cycles. So in the example that we started last time, our clock cycle is 200 picoseconds. So so each kind of on this timeline, the space between two ticks is exactly one clock cycle. And obviously, we are looking at multiple clock cycles. That's why it's called a multi-cycle diagram. And here we have our add instruction. It's pretty boring, right? Nothing particularly interesting happens with this add. But then we have BEQ, and so it is executed, normally, and then we need to decide whether the branch is taken or not. And before that happens, we don't know which instruction to fetch. So if we assume that we threw this additional hardware and so oops. So this stage of BQ, right, which happens here between 400 and 600. This is the ID stage of this BQ instruction. Okay, and if if we added this additional hardware that determines whether the branch is taken or not, we will know here at time 600, we will know whether with the branch is taken or not. So we would know whether the value from register 1 and register 2, whether those values are the same. And given that knowledge, we will know which instruction to fetch next. So for example, if and this is just their amount of offset in the PC that we will be, so it's the value added to PC plus 4 that we will be doing if the branch is taken, right? So if the branch is not taken, we will execute this next instruction, whatever that is. But if the branch is not taken, but if the branch is taken, right? So we will go here to this instruction. And so this simple approach that we are discussing right now says, well, whether branch is taken or not doesn't matter. We always wait until we know what the outcome is, and then once we know whether the branch is taken or not, we fetch the corresponding instruction, which means that this instruction fetch for the next instruction, right? This is IF. will happen between 600 and 800. That right, because we cannot do it earlier, right? We cannot do it before the ID stage of the BQ is done, because we would not know whether the branch is taken or not. And that means that, well, we have a bubble, right? We have this instruction that we essentially call NOP, right? It's an instruction that does not affect the state of the processor and memory, right? It's just instruction that does nothing. And so here we see why this approach would have a stall on every BQ instruction, right? Again, it doesn't matter whether the branch is taken or not. We're just gonna wait until we know this, until this time 600, and then and then we know which instruction to fetch, and we will fetch the next instruction. Okay, so there's a question. The ID stage, that's where it decides to take their branch or not. Yes, we assume this, right? It's not always the case, so please be very careful, because we assume that we add hardware to do this in the ID stage. If we didn't do that, then it would be even worse. It would be one additional bubble, right? Because then, if we didn't have that additional hardware, we would only know whether the branch is taken or not at time 800, and we would be fetching our next instruction, starting from time 800, and that means there would be two bubbles. Okay, so by throwing this additional hardware that makes the branch, that allows us to know whether the branch is taken or not one stage earlier, we were able to eliminate one bubble. And bubble is basically when we have to, it's a slot, right? So it's a slot that could have been an instruction, but we are wasting it. We are executing the instruction that has no effect on anything, right? Just to get our timing straight, right? We cannot. If you imagine, this next instruction, if it were a real instruction, it would have its IF stage here between 400 and 600. But in this approach that we're discussing, that can never happen. We don't know which instruction to fetch, because we don't know what the outcome of their BQ is going to be, whether the branch is taken or not. So how come at time 400 can we determine which instruction to fetch? What would be the address of the instruction, PC plus 4 or PC plus 4 plus 40? Okay, if we don't know the outcome of the branch. Making sense? When installed, does it install only the dependent instruction or every instruction after the bubble? Well, you have to think in 4 dimensions. You have to think with the time dimension in mind. All other instructions. So it's like this is our timeline, right? So we just make a decision at every moment of time, right? So here we are making the decision. All right, we are fetching instruction BQ. Here we're making this decision. Oh, we are fetching our next instruction. No, we are not, because the previous instruction would BQ, so we are just fetching NOP. Here we are making this decision. All right, so here we know the outcome of the branching of BQ, so we are ready to fetch our next instruction. And that would be the actual instruction that is going to be executed given our branch decision, take or not take. So it's one decision, it's, well, multiple decisions, but it's linear in time. So of course we don't see all future instructions, right? So we just fetch instructions, one at a time from our instruction memory. We have no way to look into the future. Does NOP stand for anything? Yes, NOP stands for, and it's very common in pretty much any assembly language that I have seen. It's the same. It means no operation, right? So, and usually it has their instruction code of all zeros, like that. So it's basically an instruction that is guaranteed to have absolutely no effect on anything. Okay, so of course it's not by itself, it's not useful because it's not doing anything, but it is helpful when we need to, kind of pause, right? You cannot pause a processor, right? You cannot let it wait for 200 picoseconds, right? The processor gets its clock, right? We know, this is the, this is the clock, and you cannot, stop the clock. Well, I mean, you can if you put the processor to sleep, but then it's not going to be executing anything, right? So you cannot, your processor, it just, it just doing its work. It cannot stop it, and therefore, if we want to effectively pause it, we have to do this in a sort of artificial way with a NOP instruction. All right, and so what can we do? Oh, can you propose a better approach? So this I think some of you, all of you, can probably guess. Is there a better way than this one? Okay, what would be the better approach? That would all right. So what would be the so here we have a bubble. We are wasting one clock cycle regardless of whether the branch is taken or not. Okay, and branch prediction. Get Malik here for speed erase. All right. Anyways, so well, what is branch prediction? Someone mentioned it. Predict if the branch is taken or not. But how do it's challenging. Like, how do you predict it? Okay, so well, what you mean might be a simple version of prediction, but instead of having this knob after every single BQ, whether the branch is taken or not, I think the straightforward solution is, well, we only have two outcomes, right? Taken or not taken. And now we have one bubble here and one bubble here, right? So no matter whether taken or not taken. So we can do better, right? We can say, well, can we kind of say that we read the next instruction, this instruction, right? We fetch this instruction, which would be equivalent to betting that their branch will not be taken. And if our bet is successful, then there will be no knob, right? So we would be able to eliminate this bubble if the branch is not taken. And if it's taken, it's still going to be one bubble. We would be no, it would be no worse than our current performance, the performance of our current method. So this is the simplest way of predicting, if you will, right? It's not a real smart prediction, right? Because typically when we say predict, it means we have some information and then we make a reasonable prediction, right? So I look at the sky and I'm thinking, all right, so I predict there will be no rain in the next 20 minutes, right? So it's not just a wild guess, it's an educated prediction. But here what we are talking about is a very simple, very very non-intelligent prediction. We just say, well, I predict it's going to be, the branch is not going to be taken, and then basically I have a 50-50 chance to be right. Okay, so yeah, and someone's saying they were looking at types of branch prediction during last lectures, and there are quite a lot. Yes, there are quite a lot, and of course, the real smart prediction is what we are going to call dynamic prediction, right? Which actually takes into account the history and tries to kind of do what we usually mean when we say predict, right? The simple prediction is just saying, well, we just predict. It's like me, not even looking out the window and saying, well, I predict there will be no rain in the next 20 minutes without having any clue what's going on outside. Okay, so it's a kind of prediction, not very intelligent one, but it's a kind of prediction. And it turns out that for our control hazards, it would actually be better than no prediction at all. It would be better on average than this method that we described now. And so here we are with branch prediction. So the idea is that We want to minimize stall penalties because as our pipelines get longer meaning the number of stages, right? And here's one note about the length of their pipeline. So in our case, the length of the pipeline is five stages. Why would anyone want to have more more stages? Can someone tell me? It's actually a good question for open-ended question for a test. I don't know. Maybe it's not going to be on the test, but yeah, let's see if anyone has any ideas. Why would I want to have more stages in my pipeline? To reduce clock cycle, exactly, or to remove unbalance, or imbalance, right? So here are our five stages: one, two, three, four, five, right? And recall that the hardware that works at each of those five stages is different, and it actually takes different amount of time. So recall previously in the beginning of this chapter, we were going through some examples. So this might take 200, this might take 100, this might take 180. This might take 70, and this might take 350. Okay, for example. So if we, given that, what would be the clock cycle that we would be forced to select? Anyone? 350, exactly. 350, right? We have to account for the longest stage. So, and then the total then there we will be getting 350. So we will be getting one instruction done every 350, whatever time units are. Let's say picoseconds. All right. So then what can we do to make this better? Well, we can say, well, maybe we can split this stage here into two stages without making any other changes. So instead of five stages, we now have six stages: 200, 100, 180, 70, 175, right, and 175. Okay, so what is their clock cycle now? The clock cycle now is 200, right? So TC is 200 now, and 200 is quite a lot better than 350. So it looks like there's clearly, and now since clock cycle is 200, we are saying, oh, we're going to have, one instruction done every 200 picoseconds. So our throughput is going to be much, much better. Okay, so it looks like there is clearly an incentive for making, pipelines longer and longer, so that each stage is very short. All right. So what stops us from, making our pipelines too long? What is the limiting factor? Would why would we want to stop splitting our stages at some point and say no, that's it? We should stop. We should no longer increase the length of our pipeline. Anyone, please? Cost. Yeah, cost is one thing. I I would say uh, probably not the leading. Of course, it has its effect. I think there's a clear technical reason here. Is there incentive? Is there an incentive to not stop pipelining? Too many individual separations of hardware. Well, this is true, but I'm I can have another reason in mind. Lose track of hardware locations. Well, no, not really. Like if you design the hardware, you would know where things are. So think about the pipeline.
Data
The more.
heads.
Yeah, go
Would
ahead.
you have a higher chance of? I mean, not a higher chance. Would you have more of a problem of dealing with data hazards if the pipeline is much longer?
Exactly,
Okay.
exactly. So you would, the longer your pipeline is, the more stages, the higher the probability of hazards, and then the, the larger the distance between, different stages. So you may have to do, more bubbles. Okay, so yes, each bubble is going to be smaller because of the clock cycle that is smaller, but you might have to do more bubbles, and so that would definitely hurt, right? So and that's why it, of course, limits, along with the other factors that you mentioned, like complexity of hardware, which translates into cost. And yeah, so I just wanted to, and I think one of their problems, one of the textbook problems for this homework is kind of related to this. They're asking like, what if we split this stage and ask you to compute something along the line? So I'm glad we talked a little bit about it. All right, and here, oops. Uh, so that's what we mean when we say longer longer pipelines right here, all right? Pipelines with more stages, and just as we discussed, penalties, stall penalties, which is the number of bubbles, right? For longer pipelines are more hurtful, and they can quickly become unacceptable. All right, and this still is worth pursuing, and this is our not so smart prediction when we always predict that the branch is not taken. Right? That's easy to do. No, doesn't really require any knowledge of the actual values or any history of previous execution of this instruction. Right? So we just always say we predict that the branch will not be taken, so we start fetching next instruction. Here's an example. Right? Here's our add instruction is the same, BQ is the same, and then we start fetching the next instruction, kind of betting on the fact that this is the instruction that will be executed, right? So if the branch is not taken, this instruction is going to be executed next, and if our prediction is correct, right? If we didn't even look out of the window, look out the window, and we predicted that it's going to be rating, and it is in fact rating, right? We are we are in good shape. So there's no bubble here, and that clearly is an improvement over our previous method because at least in some cases we are able to proceed without stalling our pipeline. So here it is. And of course, if our prediction is incorrect, well, we have to throw out the instruction that we fetched. So this instruction, all right, is not going to be executed, and therefore, we have to basically throw out this instruction. So this used to be our LW instruction, which we kind of discarded and we turn it into NOP, right? Because we know that this instruction should not be executed. All right, so we have to convert it to a NOP so that it has no effect, and then start fetching their instruction at their target address, right? At PC plus 4 plus 40, this is the instruction, and it will be executed next, so we need to start fetching it. So there's a bubble, but in the previous case, there was a bubble no matter what. There was a bubble every time we executed this BQ. Here, we have a bubble only when our wild guess turned out to be incorrect. Are bubbled filled with forwarding? No, it has nothing to do with forwarding. Well, if anything, forwarding is an attempt to reduce the number of bubbles. A bubble is an instruction that you start fetching, and then it turns out that it is not ready to be executed, or it should not be executed, and then you forcefully kind of change this instruction into NOP. And basically, for the processor, it means it's a wasted time slot because NOP, like we discussed, has no effect on the processor or memory. So yes, if you predict incorrect, it's a bubble, okay, right? Because we only know whether that the branch is, whether branch is really taken or not here at time 600, and only at time 600 will we know that our prediction that the branch is not taken isn't correct and the branch is taken. Right, so we cannot possibly start fetching the instruction at either this or instruction earlier than time 600 because before time 600 we don't know that we were wrong and we wouldn't know that their branch is taken. All right, and of course, so this is an example of a pretty dumb branch prediction, which still is useful as we saw, right? But we can go with slightly more complicated. So and the more complicated approaches, they fall into two groups: static and dynamic branch prediction. Static is still not very intelligent, but better than our baseline prediction, right? We make our prediction based on typical branch behavior. So what does it mean, typical branch behavior? Well, it means that we do not take into account the history of how our specific program is executed. We just make some prediction based on what a typical program does, or typical loop does, or typical if statement does. So for example, for loops, we can say we predict that the backward branch is always taken and that the forward branch is never taken, right? So what does it mean, backward and forward? Well, if we think about it, right, here's our BQ, and it might send us back or it might send us forward, right? So typically, if we have a loop, then we at the end of the body of the loop we have this BEQ instruction that sends us back to the beginning of the body of the loop, and we know that a typical loop will be executed many times, and that's why it's going to make sense that backward branches are taken, right, because we expect the body of the loop to be executed many times. So we are more likely to actually take this branch than not take it on average for a typical program. And then for the other for forward branches, we going to be predicting that it's never taken. All right, and so that's one approach, and then the second approach is called dynamic branch prediction, and it's a lot more complicated, of course, but it's a lot more realistic. And that means that we actually have some instrumentation to measure how our actual program is executed. So, for example, for each branch instruction, we keep a history, and we count how many times that instruction took the branch and didn't take the branch. Okay, so this sounds like, well, I don't know if it sounds simple, right? It can be. It's just this one line of explanation. But can you imagine the consequences? Like, we're gonna have this table, which is gonna be huge, right? For all branch instructions. So, for example, if I just mark instructions, with just line numbers, 2, 7, right? I don't know, 13. So each is some kind of branch instruction, right? So for every single branch instruction in our program, we're going to have an entry in our, in this table, like 25, whatever, right? And for each branch instruction, we need to have their stats. We need to have the statistics, number of times taken, and number of times not taken, right? So initially, of course, it's going to be all zeros, and then we're going to have, we're going to be collecting the statistics, like, taken, this branch was taken 2 times and not taken 10 times, something like that. So it's very, very taxing, right? It adds a lot of complexity because you have to collect the statistics, right? But that allows you to do an intelligent prediction, and of course, it's never guaranteed to be correct. It's like if you're if you're investing in a stock market, right, you always read this disclaimer that, well, their future performance, the past performance is never, a guaranteed predictor of their future returns or future performance, right? So, if a particular stock jumped, 500% in their next 12 months, there's no guarantee it will jump another 500% in the next 12 months. Okay, so it's the same stuff here, right? You can hope that it's going to happen, but it is not guaranteed. But it's better than nothing, right? So, for branches at least, we can make our prediction based on the statistics, right? If we see that for this instruction, it's the branch is not taken more often than it's taken, we can predict that it's not taken, and of course, then we might come to a situation where we were wrong and we thought the branch would be not taken, but it was taken. So we have to update our stats, right? So then it becomes 3, and then we are wrong again, and then it becomes 4, and then it becomes 5, and eventually it becomes 11, and then we have to change our prediction, right? Because now from the stats we see, oh yeah, this instruction is in the past was taken more often than not taken, so we're gonna start predicting a different behavior, right? Based on this. As you can see, it's a lot more sophisticated system, this dynamic branch prediction, and it makes assumptions of the future behavior that is based on their observed past performance, and it's never guaranteed to be correct, so it can still be wrong, and we might, if our prediction isn't correct, we would still have to stall their pipeline, refetch the instruction, update our history, and go like that. And yes, it uses a lot of memory because it has to be done for every single branch instruction. Okay, so it's pretty, but it's neat. So I think from the engineering standpoint, it's a pretty neat trick. Is it faster to reference the history of branch instructions than just not using a prediction? Yes. So actually, it is known that dynamic prediction, is actually on average is working better than static prediction. Okay, so it is more accurate, and of course, it's a lot more accurate than our simple approach: always predict, not taken. Right? That's the worst. So among 3 options, this is option 2, this is option 3, Roman numerals, and this is option 1, right? Always predict, not taken. So, option number 1 is there doesn't really take any investment in terms of hardware, but it's also, the least accurate. Number 2 takes, a little effort, but it is better than number 1 in terms of performance. Number 3 takes a lot more effort and a lot additional hardware and memory, and but it is also more precise. Yes, in fact, it sacrifices memory for speed, and extra memory, of course, means cost. Okay, so if you have to dig it, this memory that is used here, it's for the user it's useless, right? Users do not see that memory; it's not available to them, so you have to spend money on that memory, and it's memory inside the processor, which is extremely expensive in relative terms, but it is a lot more expensive than your RAM, uh, and it has to be inside the processor, of course. But so it's an extra cost, extra area on the silicon die, but it is speed exactly. All right, so here's our pipeline summary here. Basically, why we want our pipelining is because it improved performance. Their individual instruction is not going to be executed any faster, but the throughput, the average number of instructions per unit of time, is going to be much better. And of course, nothing is free, so it comes with the strings attached. The pipeline and architecture is subject to hazards. 3 types of hazards: structure, data control. Structures, we just have to, structural hazards, we just have to redesign our hardware. Not much anything else we can do. But data and control, hazards, we can actually propose several different approaches to how to mitigate those problems, at least to some degree. And so instruction set design, our ISA, of course, affects the complexity of pipeline implementation. So if you have less regular formats of instructions, of course, their pipeline is going to be a lot more complicated. Imagine x86 and its instructions that have a length of 1 to 17 instructions. So can you imagine you have to read the first word of the instruction, uh, the first byte of the instruction, it's 1 to 17 bytes, and then based on that decide whether you need to read the next byte of the instruction or not. And you never, it takes several bytes of the instruction that you have to read first before you know how long your instruction is going to be. And then can you imagine the decoding part of this instruction? In our case, we didn't have any decoding. Well, we had a very simple decoding hardware, right? Because our all instructions and MIPS are 32 bits. It's not at all that simple in x86. So obviously, ISA affects the design of the pipeline. All right. So what do you think comes next? What else do we need to discuss regarding pipelining? Hopefully, it seems all clear and logical so far. But what do you think is coming up? Exactly. We have to implement this, right? All those nice things that we discussed, we have to implement them. And here we are. Their pipeline data path, right? Not the simple data path, but this one is actually no different. So it's not a pipeline data path yet. Can someone tell me why it is not? So if you look at it, it's basically our previous non-pipeline data path. So we cannot call it pipelined. Why? There are arrows that go backwards. Well, those were, so you are talking about these two arrows, right? The ones that are in blue. So missing control, that's a good point, but it's just not shown here, right? So all control signals are in place. So they're just not shown here. So good guess, but that's not exactly what I meant. So for the arrows, to make figures more confusing to you, usually we know that blue means it's a control signal. In this particular figure, blue just kind of highlights the arrows that go right to left. Okay, they are not control signals. They're just two cases that are shown here, where our arrows go not from left to right but from right to left. And they are the same as in their non-pipeline data path, right? Because once we computed the address of the instruction to be executed next, it has to be loaded into the PC, right? So it's this it's this arrow or this connection, and once we computed their value to be written into the register, or once we read the data memory that we want to load into the register for LW load word instructions, we have to write it back. So this is their link back to their register file. Okay, so that's not really the reason why this is not a pipeline need. Missing the memory between the steps. Excellent. That is exactly why this is exactly the major reason why this is not a pipeline data path. Because and how you could have guessed, if I assume the person who gave this correct answer, they didn't look at the textbook yet or at the slides, so they just guessed it correctly based on just the logic of the diagram. But recall that in our non-pipeline data path, we had one instruction that would go through all the hardware on this in this processor circuit, in this processor diagram, from left to right, and we would only have one instruction occupying the processor at any moment of time. And with the pipeline designed, we have multiple instructions that are at different stages of their execution and that are occupying each its own part of the pipeline, each its own hardware. So one instruction might be decoding, so it would be doing their register read, and another instruction might be doing memory access, so it would be here doing their data memory read, and they are two different instructions with two different opcodes. And this design where we have this single instruction code, right? So this is all the instruction code, right? And we see that it is actually affecting all the stages. So obviously there are no provisions to keep multiple instructions at the same time for different stages. So that means that you need some kind of buffers between the stages, right? So here you need something to store here and here, right? Between all the stages, you need some kind of buffer, some kind of memory that would remember the instruction that is executing at this particular stage. So we let's say we have some instruction that is called add, and then initially, when we just read the instruction, it went through IF stage. Then this buffer here will contain everything related to this add instruction. And then next clock cycle, our instruction moves forward to the next stage, right? To this thing. So add is now here, right? Everything related to this instruction, all the control signals, the instruction word, the opcode, everything. And the next instruction is read. So let's say the next instruction is OR. So now OR is here, and add has moved to the buffer for the next stage. All right, and then this process just continues, and we are going to have multiple instructions, and each would be stored in the buffer, and each would kind of move from left to right in this data path. And so the normal flow of how data moves in this data path, of course, is left to right. Right. This comes very natural to us, hopefully already. So if we have anything that violates this, it would be right to left, and so right to left flow would lead to hazards, right? It is the problem because now we imagine that we have value read from data memory here, and for the instruction that is at the mem stage, and when it needs to write back the data, hey, but our register file is already occupied by an instruction that is two instructions later. Okay, so this write data would not write data to the correct register because the right register is coming from their instruction that is two instruction ahead. Okay, so and that's why it's a hazard. All right, it's something that would create a problem. So for and yeah, so this is the why it says WB, because it's the value from the right backstage. Okay, and here it says mem. Well, it's not necessarily mem, but it's the result of this of this either this address, right, that is loaded into PC, or we might also have a case there when we have their ALU that needs to the output of the ALU that is routed back through this multiplexer and back. Okay, so it's this path. All right, so from the mem stage, right? So this is the mem stage, and we might have value, all right, that is the result of the ALU, but that it doesn't go through their data memory, but just follows this path. And here's the link from right to left. Okay, so we have to find a way to deal with this problem. All right, and as we already discussed, that's pipeline registers, right? Without them, we're not going to be able to make the pipeline design. So at the first stage, the only thing that we add to our simple non-pipelined design is just we add those pipeline registers, right? So if I ask you, based on this figure, well, this IFID. Well, first let's do the notation. It's their buffer, and the buffer is just a register, just a memory, right? Between stages IF and ID. And obviously we only need those buffers between the stages, so we have 5 stages, hence 4 registers, 4 buffers. And the notation is as I just described, IFID between IF and ID stages. And it's just the memory. Well, if I ask you, well, how many bits does this IFID register have? 32. Why? Well, instruction is 32 bits, no doubt about that. But this register stores not just the instruction word, but also this. How large is this? This one is 32 exactly. So all in all, it's 64, right? So this one is 64 exactly. And you know, it can vary. We will actually see that this is not everything that we need. We also need to add control signals to our register, so our registers will be even larger. And so it doesn't have to be the number which is a power of 2, right? So it's not going to be necessarily 64 or 128. So it can be like 67 or 75 or any number of bits. So to answer this question, just look at at all their buses and other single signals that go into this register, and just sum the number of the number of them, the number of essentially different wires that go into. And yeah, so that's that. And yes, and different buffers may have different lengths. All right, so we can actually. So what about IDEX? How many bits? All right, let's see. 32 here, 32 here, 32 here already marked, and 32 here. Right. So the convention that they use in these figures, if the output is at the same level as the input, it kind of means it's the same thing, right? So it's their so essentially it's going to be PC plus 4 right here. So it means it's going to be PC plus 4 here. So it's 64, 128. Is that? Yeah. So I agree, 128. So you see, they can totally have different lengths. All right. So that's good. We need those buffers, and so now we have to talk about their single clock cycle versus multi-clock cycle. We have already seen multi-clock cycle diagrams, so let's give a formal definition. So a single clock cycle diagram shows us uh, a snapshot of their pipeline at a given cycle. Okay, so it's a snapshot, it's a moment in time. And in this diagram, we show which resources are used and how. Whereas multi-clock cycle diagram that we have seen before shows, like their time projection. It shows how the pipeline is used over time. Remember, there was a time dimension, there was a time axis in our diagrams. So, both are useful. Okay, so they allow us to reason, to see different things. They allow us to, get the full picture. So you need to know both the single clock cycle and the multi-clock cycle diagrams, of course. And so to begin with, we're going to look at their single clock cycle diagram for the load and store operation. So here is their instruction fetch first. All right, so we show here their kind of the length of their instruction. in time, but it's a snapshot, so it's one moment of time. Okay, so well, basically we show this. They're not even the time, but they're the limits of their hardware that is used by this instruction. Okay, so that would be a more a better way to describe it, right? So this is IF, right, and it's a LW instruction, but IF is going to be the same for all instructions. So the hardware that is used is shaded with this blue, color, dark blue, and if only half of their component is shaded, it means it corresponds to whether it's read or written. If the right side is shaded, it means the component is read. And of course, it only applies to memory, right? Because we can only read memory. That's why, the adder is shaded all the way through. The multiplexer is shaded all the way through because we cannot read or write them. But memory, we can read and write. So in this stage, instruction fetch, we read from instruction memory and we write to this buffer. That's all that happens at this stage, and that's why the left half of IFID buffer is shaded. And that's all that is happening here, right? So, and like I said, this notation here, this bracket shows which hardware is engaged in this first stage, right? It's the PC, this adder, instruction memory, and IFID. And we see that indeed incrementing PC happens very early, happens basically synchronously with the read of the current instruction, and the address of the next instruction is going to be produced by the end of this cycle, of the IF cycle. All right, so then ID stage, right? We read this IFID, okay, because there.
Did all of you guys get kicked out?
You just accidentally closed the meeting.
Yo, yeah, did someone close the meeting?
Yeah, what happened? I thought I closed it.
Oof. I thought it went dead or something like that.
Yeah, I just thought my WebEx crashed. Like, just abruptly ended.
He probably confused as hell right now. Professor, I mean.
Where's Professor now?
Professor, you're muted.
Yeah, thank you. I noticed just now. All right, and yeah, this is exactly what happened. One of the panelists left and ended the meeting for all of us. And I mentioned several times already, asking, begging the panelists not to do that. There's no way we can technically prevent it because we have to make panelists co-hosts, but their co-host gets the power to end the meeting for all. And we ask people not to do it. All right, so it is becoming pretty disruptive for the lecture. Okay, so please, if it keeps going on like that, we just stop doing panelists. Okay, I just don't see any other way. And Cheyenne, even do you read emails from Cheyenne? She added even a paragraph saying, please do not end the meeting for all. Just leave the meeting if you no longer want to be here, but do not end it for all if you're a panelist. So please observe this. All right, it's getting honestly pretty annoying. All right. But of course, if someone wants to teach this class instead of me, I wouldn't mind. Yeah, maybe one of the people who's getting an A. Well, there are many people who are going to be getting an A, so we have a good choice here. Yeah, and good point. Panelists are really expected to stay all the way through and not leave, halfway. Well, not halfway, but still 40 minutes before the end of the lecture. All right, so we are back. Hopefully, sorry about that. I wasn't. It was pretty unexpected. All right, and we were talking about their ID stage, right? Where we read IFID and we read register file and we write into their IDEX, right? And IDEX would need to contain all the information needed for this instruction for all the subsequent stages. So it's not just their their extended immediate field, and it's not just their instruction instruction word, but it is, for example, also both values read from their register file, right? Because we might need to, do something with those values, add them or subtract them, and we should serve those values then to the ALU, and that means that we have to save them in our buffer register. Okay, and yeah, I know that person won't even know what they did because they left. Well, hopefully they have friends who tell them. I don't even know what that person is. I don't think I can I can determine this, unfortunately. Otherwise, I would just reach out to that person individually with with my little request not to do it anymore. All right, so here is the execution stage. Again, it's very similar. We read this IDEX register, we do our multiplexer ALU thing, and we write into EXMEM. So ALU is used for this instruction. What does ALU do at this stage? Someone, please? Well, it is a LW instruction. ALU computes the effective address that will be then used to access data memory. Okay, and it's not a branch instruction. That's why you see this shift left to and this adder. They are not, they do not have this blue background, which means they're not used for this instruction, right? Because it's not a branch instruction. All right, so this is just to help you understand the notation used in this in those diagrams, and hopefully those diagrams now really talk to you, and they make sense. So mem, it's an LW. That's why memory is read, right? So we load from memory into then register, and as usual we read ex mem register buffer, and we will write the result of this stage of this mem stage for this instruction into the mem wb register for our instruction, right? So of our thing. All right. So then WB, that's an interesting one. So let me. Okay. So here it looks like it's the same. We read from mem WB register, and then we write the value that was read from memory back into right. So it would be this value read, and that we stored in memwb. Now we read it from memwb, and we are reading back to the register file. Okay, is that making sense? Yes, no, maybe? How many people do we have? Do we have? Oh, we have 64 people. So, can you access can you access chat, or doesn't, or it just no one knows the answer and has no guesses? Oh, my bad. I didn't scroll. Yeah. All right. So yeah, you can. Were there any suggestions? So people are saying, yeah, makes sense. Okay, cool. Although that is not the correct answer. So the correct answer should be, it's not. Well, it's making sense, but there's an error here. Can someone point out what the error is in this diagram? Yes, but won't there be data hazard if it's pipelining? Exactly. This WB is broken because we are writing back the value. So the right data here is going to be the correct value that LW read from the memory, but it's going to be writing back to the register that is determined by the instruction two instructions ahead. So there's LW and then something, and so we are here at the WB stage, right? So next instruction would be at the mem stage, and next instruction would be at the ALU stage, and next instruction, oops, not ALU, we call it EX, and next instruction would be at ID stage, right? So whatever that instruction is, and here we have this instruction. Let's say T1, T2, T3. Okay, and so the right register that determines into which register stuff is written will be coming from this instruction, right? Because this is our ID stage, right? If we break it into stages like that, so this is EX, this is mem, okay, up to here, and this is our write back. So this instruction at ID stage is this add instruction that has T3. So this write register would be T3, okay, and not the register that was here in the LW instruction. Okay, it's gonna write to their own register. All right, because we messed up this. Well, no, it was intentional, of course. So no, it's not bubble. We just need to fix the error. It's the flaw in our design. So this design is flawed. We can fix it. Okay. So how do we fix it? Any thoughts?
I have an idea.
Yeah, go ahead.
Maybe so like the instruction is pointing to the right register. So maybe instead of doing that, it would just like go through all the maybe it'll go straight to like actually I'm not too sure. I think it just it just skips every step. It just doesn't connect the instruction to right register, and then it will somehow come back and then write to right register.
Exactly.
to do
You spotted the problem exactly correct. So the problem is in this. So everything related to our LW instruction is in this register at this moment of time, right? And if the right register is not here, it's lost. There's no way for this instruction to remember that it was supposed to write into S0. So the solution is, well, we need to, carry this, this destination register, this S0, with the instruction, so that when it needs to write back, we can, sort of do this, instead of just this being write register, we can do something more fancy. We can have a multiplexer, which is saying, well, what is this write register? Is this the one coming from the instruction word, or is this the one coming from our write back stage? Okay, and we make this, this multiplexer. Okay, but the key is we have to change our buffers to extend our buffers so that this value is stored, because if that value is not stored, there's no way we can recover it. Of course, we cannot read the instruction again. It wouldn't make any sense, right? The instruction was read, and we just lost some essential information about this instruction along the way, and we just want to prevent this. Okay, so this is exactly their solution. Where are we? Oops. All right. So this is their, their not too formally, but this is kind of the sketch of, oh, okay, so from this instruction word, right, we need to, kind of in addition to keep their information about their write register, right, and kind of keep it throughout their the rest of their cycle, of the execution cycle, so that if turns out that we need it, we need to write the register. We know which register to write to. So and it's a sketch. So if we do it like that, we don't even need a multiplexer, right? So we can come up with a simpler design, right? But this solves this problem, okay? Because now we have we always store the right register. So instead of multiplexer that makes this decision, which thing to route, we just say, all right, we're just gonna keep this right register in the buffers, for all remaining 4 stages of the execution. So in all 3 buffers, there will be this little section, five bits, that stores the right register. Whether we need it or not, for some instructions we might, for some instructions we might not, but we have it just in case. And for instructions where for which we need it, it's gonna come very handy. So the register to write to does not come out of the registers box. It comes out of their instruction word, okay, because it is encoded in the instruction itself. Remember those RS, RT, RD stuff? All right, so that was LW instruction. So, just to realize what we've done, so we looked at a single instruction, and we had a snapshot of the processor at each stage. So it was one cycle at a time. First cycle, second cycle, third cycle, fourth, and fifth. All right, all 5 cycles, one cycle at a time, that show how load instruction would go through the entire pipeline, from the time when it entered the pipeline, when we fetched this instruction here, to the time when it left the pipeline here, when it is done and the instruction is pushed out of the pipeline. And the same stuff for another instruction store. So it's SW. The first 2 stages are going to be the same, so we are not showing them because they are exactly the same, IF and ID. The EX stage is the same, I believe, but they still show it, right? Because we read their buffer, then we compute the address, the effective address for the memory, store it in their memory, in the buffer, EX mem buffer, and then this stage is clearly different because for store W we write to the data memory. So see how this left half of data memory is shaded, because we are writing to that data memory. And then write back is also different. In write back, we don't have to do anything for store W, because there's just no work to do, right? We are writing from the register into the data memory, so no registers to write. And the multi-cycle pipeline diagram, right, is just a different view. We can do the same stuff with the instructions, but we show, each clock cycle, right? CC stands for clock cycle. Uh, multiple clock cycles on the same diagram. So this is essentially, our time dimension. And this is our program. So instructions execute from top to bottom, and we show in for each instruction which resources it uses, using the same notation that we did in the single cycle diagram. So LW, when it reads instruction memory at their, so this would be their for this instruction it would be the IF stage. It reads instruction memory and writes to their buffer, and then next clock cycle it reads from the buffer and reads from the registers and writes to their next buffer, and then CC3 it reads from this buffer, uses ALU, writes to this buffer, and so forth. So you can see how the instruction enters and leaves their pipeline in a more compact way in just a single diagram that shows pretty much the part of the entire program. Okay, so again, the notation is when we are writing, it's the left part that is shaded. So LW writes to the register file. This is the WB phase, and when we read something, then we we highlight the right part, the right half of their memory. So instruction memory, we only read, and that's why we only would have their right part of their IM highlighted. Whereas data memory, you see, for load word, we read, and for write, for store word, well, it's not here, so we don't do anything. And yeah, so that's, and I think, yeah, there's a mistake, right? See how they actually, this one was supposed to be with the right half highlighted, not this one. This is wrong, right? This should be, add instruction doesn't access data memory, right? So this should be all white background, and instead this should have right half highlighted in blue. So it's clearly a a little mistake. And the dashed thing here, right? So see how this is dashed? It means this unique case for the register file where it only takes one half of our clock cycle to read or write, and that's why we see that we've seen before that we can read and write at the same time, and that's why when we are reading in the second half of the cycle, right? So if we plot it here, it would be like, if we have to do the register read, it happens here, and when we do register write, it happens here, right? Like for well, for different instructions, right? So this is for this instruction, and this is for this instruction. Okay. So this is the notation, and so this is a slightly simplified form. Again, same multi-cycle diagram, but slightly simplified so that we, less fancy. And this is what you will need to do on the homework, right? Except for even easier, instead of spelling out all words, you can just do abbreviations. All right. Well, let's do one quiz at least. So. Yeah, I was hoping we would get more accomplished today, but it is what it is. So, how many cycles in total for this entire program would it take to complete? So, count from their time this first instruction enters the pipeline until the last instruction leaves the pipeline. Is there going to be a quiz for the extra credit? Question? No, that's not going to be a quiz because all questions on the test are the same number of points, so you can you can think of any single question of being extra credit. Right? It doesn't matter which one you nominate because the result is going to be the same. So pick your favorite or pick your least favorite question and think of it as extra credit. They're all worth 25 points. All right. So let's cover this. We have about 1 minute left, and then next time we're going to restart with the control. So this single cycle pipeline diagram is exactly similar to the ones that we've seen. It's a snapshot, but now it shows not just one instruction, right, which would be not unrealistic, but the entire state of the processor at any given moment of time, which means that this instruction is just being fetched, right? It is at its IF stage, whereas the previous instruction, this one, is at the ID stage, and the previous instruction is at the execution stage. So if you trace it back to the previous example, right? LW was first, sub second, add third, LW, and then the other add, right? So you see how they are positioned. LW is almost done. It is about to leave the pipeline, whereas add is just entering the pipeline, and it is being staged at this cycle. So again, single cycle diagram means a snapshot, means a given cycle, a given moment of time. And here, so we're just showing, which instruction is occupying, is using which resources of this pipeline. And it is 150, so slide 83. Next time we will start with the pipeline control, so adding more fun with all the control signals, but that's coming up on Tuesday before the Thanksgiving. And with that, let me wish you a good, well, not holidays yet, a good weekend. Enjoy your weekend. Enjoy, some sunny weather. And please, connect to us on Tuesday. Even if you're leaving for the Thanksgiving, please come to our lecture. And I'm really looking forward to it. Thank you, folks. Have a